We're going to continue along with these examples and see if we can use the alternating series tests just to get the hang of it. So if you feel like you get it, you can probably skip this video. We're just going to go through these 6 examples. All right, so notice that they're all alternating. We've got a -1 raised to n minus 1, n plus 1, n, doesn't really matter what it's raised to. Here we don't see a -1, we see a -2, but remember that -2 is equal to -1 times 2. And so if we're raising -2 to the n minus 1, we're raising both of these to the n minus 1. So this is also alternating, and this is expanded out so we can see that that is alternating as well. So all of these are alternating series. So we're going to start off with the alternating series test. And remember, if it fails the first part of the test, then we don't move on to the next test. We say it diverges by the nth term test. And if it succeeds in the first step, then we move on to the second. So the first step is ask, does the absolute value of each term, so ignoring the alternating piece, does that equal 0? And this does equal 0. The numerator grows crazy quick, and the denominator grows crazy quick, and the numerator stays constant. So yeah, that's definitely true. So that passes the first test. Move on to the next test. We have to ask, is 1 over n plus 1 factorial less than or equal to 1 over n? And that may be obvious to you, or it may not be. If it's not obvious, oops, I forgot the factorial, didn't I? A sub n is 1 over n factorial. So let's do the algebra on this one and see how it goes. We'll multiply both sides by n factorial. We'll multiply both sides by n plus 1 factorial. If you're thinking about inequalities, you should be wondering, I wonder if we're supposed to flip this from less than to greater than. And the answer is no, because n is positive. So n factorial is positive, n plus 1 factorial is positive. So we're not going to flip anything around. All right, so remember that the factorial function can be defined recursively. N plus 1 factorial is the same thing as n plus 1 times n factorial. And then we can divide out the n factorials, and we get n plus 1 is greater than or equal to 1, which is definitely true. So that checks out as well. And that means that this original series passes the alternating series test. Therefore, series converges by the alternating series test. Okay? Next, we'll ask the question first, does the individual term approach 0? Well, infinity minus 5 is infinity. Infinity squared is infinity. Infinity plus 1 is infinity. And 1 divided by infinity is 0. So that checks out. The next question is, if we replace the n with an n plus 1, is that term smaller than this term? All right, so let's give this a try again with a little bit of algebra. These are positive, so we can multiply the denominators by both sides of the inequality without fear of flipping the inequality symbol. N plus 1 minus 5 is n minus 4. We can subtract the 1 from both sides and then expand out the polynomial, the binomial squared. The n squareds can get subtracted out. We can subtract 16 from both sides. We can add 10n to both sides. And we get 2n. So n is greater than or equal to 4.5. Well, that might not be true when it starts, but eventually n is going to get bigger than 4.5, and it's going to stay bigger than 4.5. So it doesn't have to be always, just eventually and forever after that. So yes, that's going to be eventually true. Therefore, the series converges by the alternating series test. Great. Too far. All right. This looks familiar. In fact, it is almost the same as the one that we just did right here, right? We had the n, negative 1 raised to the n versus negative 1 raised to the n plus 1. The only difference between these two series is that this one starts with a 1 instead of a negative 1. So we found that the last one converges by the alternating series test. Since the absolute value of these terms is also 1 over n, we're going to do the exact same thing. So I'm going to say C above. All of that's going to be exactly the same work. Okay? Remember, we now know that this simple alternating harmonic series does converge, but we don't know what it converges to. We'll figure that out eventually, but for now we'll just have to be content with the fact that it does converge. All right. Again, step 1, ignoring that negative 1 to the n, or n plus 1, or whatever. We just look at the nth term, and we take its limit, and we find that it equals 1, which is not equal to 0. Wah, wah. Therefore, the series does not converge. It diverges by the nth term test. We don't move on to the second part of the alternating series test. We just say, oh, we're done. It diverges by nth term test. Here we've got, again, that negative inside the base of the exponent is what makes this alternating. So ask the question, what happens if we ignore that negative and we take the limit as n approaches infinity of this thing? Well, that's an infinity over infinity, but what sort of infinity? Our hierarchy of infinities says that n grows to infinity much more slowly than exponentials. So the numerator is small compared to the denominator. No need for L'Hopital's rule, although L'Hopital's rule would indeed work. Okay, so this series passes step 1 of the test. Step 2 of the test is, does the n plus first term, so replace all of your n's with n plus 1, always less than or equal to the nth term? Okay, so that's a question we have to try to answer. Well, let's get rid of the fractions. We'll multiply both sides by 2 to the n. We'll multiply both sides of the inequality by, minus 1. And we'll also multiply both sides by 2 to the n. And then we can divide out 2 to the n minus 1, because each of these has at least n minus 1 factors of 2. So that's going to leave us with n plus 1 on the left side. That's going to leave us with, I left out the n here, didn't I? 2n on the right side. Okay, so we can subtract n from both sides, and we'll see that n is greater than or equal to 1, which is true. So that means that this series passes both parts of the AST. Therefore, the series converges by the alternating series tests. Now this last one is a little bit harder. We don't have the nth term in closed form. We might be able to figure out a way to write it in closed form, but let's just ask the question, if we look at this sequence of positive terms, we're going to take the limit, this is going to be 1a. We're going to take the limit as n approaches infinity of, let's see, this is 2 over n, right? The numerator is always 2. The denominator is going up by 1 each time. So that's going to approach 0. So that is part of the terms approaching 0. Let's take a look at the negative ones. The negative terms, well, you'll notice that that's doing pretty much the same thing, except this time the numerator is 1. So that is also equal to 0. So because both of these sequences are approaching zero, one from above zero and one from below zero, we're kind of zeroing in, haha, on zero. We can say for sure that this passes the first test. The limit as n approaches infinity of a sub n does in fact equal zero, so that checks out. Okay. The next step is, can we determine whether the next term, and again, we're just focusing on the absolute value of each term in the sequence. Is it true that a sub n plus 1 is always less than or equal to a sub n? Well, let's just take a look at some of these. Is 1 less than 2? Sure. That checks out. What about 1 less than or equal to 1? Sure. That checks out. About 1/2 less than 1. 1/2 is less than, or that's not what I want to draw. Hold on a second. 1/2, that's the fourth term, is smaller than the third term. That checks out. Okay, what about the fifth term? The fifth term is 2/3. The fourth term is 1/2. Is 2/3 less than 1/2? Nope. Okay, so that's not good. But if that's the only time that happens, and then it continues to decrease from there, then who cares about the finite as long as the infinite holds? So let's keep on going. We'll take a look at 2/3. We already did 2/3. 2/3 is the last one. So we're going to go on to 1/3. 1/3 is in fact less than 2/3, right? So that checks out. And then we're going to move on to 2/4 compared to 1/3. 2/4 is 1/2. And is that less than or equal to 1/3? And we're going to find no, in fact, it's not. So we're going to alternate back and forth, interestingly, between this consecutive terms passing this test and failing this test. And since this continues on forever, we're going to say that, in fact, no, it's not true that this sequence, the n plus first term is always less than or equal to the nth term. So we actually can't use the alternating series test. AST fails to work here. We don't know what happens to this one. If it doesn't fail 1A or 1B here, but it does fail 2. So we'd have to come up with some other way of dealing with this series. I cut myself off there. You probably won't see too much of this in practice, but it is nice to consider what it looks like when a series passes the first test but fails the second.